For the Neanderthals, the skies may have foretold their fate. Their extinction was not just a matter of competition or climate. It may have been written in the stars. It may sound like an episode of Ancient Aliens when you start talking about cosmic influence on human evolution, but this theory is grounded in peer-reviewed science. The world was turned upside down, at least magnetically speaking. Around 41,500 years ago, the North Pole wandered down to New York, then across North America to Oregon, then zoomed south through the Pacific Ocean really fast to Antarctica, and stayed there for about 400 years, and then shot back north across the Indian Ocean, then back up to the North Pole. The period between 40,900 and 40,500 years ago, which aligns closely with the peak of radiation exposure, also marks the final disappearance of Neanderthals in Europe. While multiple factors contributed to their extinction, increased environmental stress, genetic damage from radiation exposure, and competition with Homo sapiens may have accelerated their decline. The important archaeological boundaries during the wider Lachon include the extinction of the Neanderthals, along with the disappearance of some of the first European modern human cultures and the subsequent widespread appearance of the Aurignacian techno-complex. Indeed, Neanderthals completely disappeared just 3,000 years after their population peaked, around 45,000 years ago. The discovery of the Stania cave pendant in Poland and a significant geomagnetic pole reversal, both dating to around 41,500 years ago, presents a tantalizing opportunity to explore connections between modern human evolution, the ludicrously rapid disappearance of Neanderthals, and environmental upheavals during this transition. This period was marked by the expansion of modern Homo sapiens into Europe, artistic innovation, and profound climatic and geomagnetic upheaval. Dated to 41,500 years ago, the pendant aligns with the peak of the Lachamp excursion when environmental conditions were most extreme. Could these seemingly disparate events be linked? If so, how might a pole reversal have influenced early human evolution and the success of Homo sapiens? A recent study, appropriately titled A Global Environmental Crisis 42,000 Years Ago, examines the environmental and climatic consequences of the Lachamp's geomagnetic reversal that occurred around 41,500 years ago, as dated from the rings of New Zealand swamp kauri trees. The auroras and electrical storms caused by the pole reversal and solar flares might have been interpreted as supernatural events, inspiring the creation of the pendant to track this phenomenon. The marks could track celestial observations tied to nighttime hunting. The vivid auroras and storms, unprecedented in human experience, could have been seen as divine or ominous signs. The pendant's worn nature suggests it held personal or communal significance tied to these events. The extreme UV radiation meant that humans would have been forced to live in caves during the day and only go out at night, so light from the moon would have been very important. Auroras, visible at latitudes like Poland due to the 5% field strength, would have illuminated the moon, prompting detailed tracking. The 59-day total on the pendant fits 2 lunar cycles, and the holes could anchor key phases, with the missing marks around hole 1 reflecting a new moon. The pendant's worn nature suggests it was a personal or communal tool, used to record these observations. The 59 marks align on the pendant closely with 2 lunar months, supporting a hypothesis of lunar notation in Upper Paleolithic artifacts. The pendant's date, 41,500 years ago, and the Lachamp excursion's celestial effects, auroras, UV increase, provide a plausible environmental trigger for lunar tracking, as early humans might have relied on the moon for timekeeping during instability. The Lachamp excursion's auroras and storms could have enhanced lunar visibility or disrupted normal cycles, prompting detailed tracking. The marks might represent a 59-day observation period, reflecting a specific event, such as auroral activity. This tradition, reflected in the pendant, is the use of punctate engravings on mobile objects, which first appeared around the same time. The pendant, a small, perforated piece of mammoth ivory adorned with a looping pattern of punctures, was directly radiocarbon dated to 41,500 years ago, making it the oldest known artifact of its kind in Eurasia. At the same time that these early modern humans were pushing into Europe and developing new traditions, the planet itself was undergoing a dramatic shift. The geomagnetic pole reversal, known as the Lachans excursion, occurred around 41,500 years ago. During this event, the Earth's magnetic field weakened significantly, allowing increased cosmic radiation to reach the surface. This geomagnetic instability, lasting for several centuries, would have had significant consequences for the environment and for human populations living through it. Increased ultraviolet radiation exposure might have influenced genetic mutations or contributed to changes in climate, disrupting ecosystems and forcing human groups to adapt rapidly. The similarity of its engravings to those on the 38,000-year-old Blanchard plaque, another Aurignacian artifact found in France, suggests a shared tradition that extended across vast distances. Whether these markings were purely decorative, mnemonic devices, or proto-notations related to lunar cycles or hunting tallies remains an open question. But a lunar cycle tracking seems the most parsimonious explanation. What is clear, however, is that early Homo sapiens were engaging in complex thought and expression in ways that had not been seen before in Europe. The coincidence of these three events, modern humans arriving in Europe, engaging in lunar tracking, and experiencing a magnetic reversal, raises intriguing possibilities. Could increased radiation from the weakened magnetic field have played a role in human evolution at this critical juncture? Some researchers have speculated that heightened cosmic radiation could lead to an increase in genetic mutations, potentially accelerating evolutionary changes. While direct evidence for this remains elusive, it is an idea worth exploring, given the striking alignment of these events. Beyond biological effects, the Lachans excursion could have also influenced early human minds and cultural expression in more subtle ways. If the pole reversal contributed to atmospheric disruptions or changes in auroral activity, early humans may have witnessed extraordinary celestial phenomena, intense auroras visible far from the poles, for instance. Such dramatic displays in the sky could have inspired early traditions, including the motifs seen on objects like the Steinia pendant. The looping pattern on the pendant has been compared to lunar analemma, a representation of the moon's apparent motion over time. While speculative, it is possible that early humans, particularly those who were developing an interest in tracking time or celestial movements, could have incorporated observations of the sky into their cultural behaviors. Could the pole reversal at 41,500 years ago have acted as a catalyst for the emergence of new cultural behaviors? The fact that the earliest securely dated example of engraving in Eurasia coincides so precisely with this event is certainly thought-provoking. The resemblance of the Steinia pendant's engravings to lunar cycles suggests another layer of complexity in early human thought. If these markings indeed represent lunar notations, this would indicate that Homo sapiens were developing sophisticated tracking systems for time and celestial movements. While the precise meaning of the engravings remains unknown, their potential connection to lunar phases or hunting schedules implies that these early Europeans had begun to structure their activities in accordance with long-term cycles. This, in turn, might have been a response to the challenges posed by a changing environment, whether driven by climate shifts, migration patterns, or even changes in the visibility of celestial bodies due to the weakening magnetic field. The interplay of interbreeding, migration, and environmental change at this pivotal moment in history suggests that human culture was not developing in isolation, but in response to the world around it. The emergence of traditions, such as the engravings on the Steinia pendant, may have been part of a broader shift in human consciousness, one that was influenced by new landscapes, interactions with other human populations, and potentially changes in the Earth's magnetic and atmospheric conditions. The idea that radiation from space played a decisive role in Neanderthal extinction is an emerging hypothesis, but it fits within the broader context of evolutionary theories. The surge in cosmic radiation and UV exposure may have also driven major behavioral adaptations in early Homo sapiens and Neanderthals. The period around 41,500 years ago saw a significant increase in the use of caves by early humans, particularly for art, habitation, and burial practices. Some researchers speculate that this may have been a direct response to increased UV exposure, as caves provided natural protection from harmful radiation. The surge in cosmic ray penetration also triggered significant changes in Earth's climate and ecosystems. The increase in ionization and ozone depletion weakened the Arctic polar vortex, leading to major disruptions in weather patterns. Climate models suggest that these changes caused stronger storms, increased wind speeds, and shifts in precipitation patterns. This could have led to intense storms, flash flooding, and extreme temperature swings in many regions. Another intriguing aspect of this study is its potential implications for human evolution and behavior. The study notes that the increased UV radiation and climatic stress may have driven early humans and Neanderthals to seek more frequent shelter in caves during the daytime, which coincides with the appearance and widespread increase in figurative cave art between 42,000 and 40,000 years ago. This sudden behavioral shift in very different parts of the world is consistent with an increasing or changed use of caves during the Adams event, potentially as shelter from the increase of ultraviolet B, potentially to harmful levels during grand solar minima, which might also explain an increased use of red ochre sunscreen. Rather than the actual advent of figurative art, early cave art would therefore appear to represent the preservation of pre-existing behaviors in a new medium. The implications of this study are profound. While the Neanderthal populations had survived multiple climate shifts, the Lachaume event presented a unique invisible killer: radiation. Unlike glacial cycles, which they had adapted to through cultural and technological means, the extreme UV and cosmic ray exposure during this period created an insidious decline in their genetic viability. The magnetic field is in a constant state of change. It moves around, gets stronger and weaker, and occasionally reverses its poles. When this happens, the magnetic field gets weaker. Spikes in radiocarbon indicate the magnetic field weakened to around 5% of its present-day strength by 41,500 years ago. At that point, the poles flipped and the field recovered some strength before crashing and flipping back 500 years later. In fact, not only was Earth's cosmic ray shield down, the Sun's was too. Evidence from ice cores suggests that around this same time, the Sun was experiencing several grand minima, episodes of low magnetic activity. The results would have been dramatic. Solar flares and galactic cosmic rays ripped up particles in Earth's atmosphere, ionizing the air and zapping the ozone layer. Our ancestors would have witnessed shocking light shows across the sky, both day and night. The ionized air would have been a great conductor for electrical storms, increasing their frequency. Research indicates the Lachaume excursion spanned from about 42,500 to 40,500 years ago, give or take 350 years. The main phase of the excursion, when the virtual geomagnetic pole was at Antarctica and the field intensity was at its minimum, around 5% of its current strength, is dated to 41,200 years ago. Poland, located at a mid-latitude, 50 degrees north, would have experienced profound environmental and atmospheric changes due to the weakened magnetic field and pole reversal, compounded by solar grand minima and increased solar flare activity. Additionally, the study recalibrates the extinction of Neanderthals to approximately 40,900 to 40,500 years ago, bringing it closer to the peak of these environmental changes. The combination of increased radiation, environmental stress, and competition with modern humans may have contributed to the final decline of Neanderthals during this period. As discussed, one of the most significant findings of this research is the increased radiation exposure that the Earth experienced during this period. The weakening of the Earth's magnetic field to as low as 0% to 6% of its current strength during the transition phase, and about 28% during the reversed phase, allowed significantly more cosmic and solar radiation to penetrate the atmosphere. This resulted in a sharp increase in cosmogenic isotope production, particularly beryllium-10 and carbon-14, which serve as markers of past cosmic radiation levels. The study identifies peaks in these isotopes from Greenland and Antarctic ice cores, indicating a substantial surge in high-energy cosmic radiation reaching the Earth's surface. Cosmic rays are high-energy particles that originate from outer space and travel through the universe at nearly the speed of light. These energetic particles can come from a variety of sources, including the Sun, distant supernovae, black holes, and even unknown astrophysical phenomena. When cosmic rays reach Earth's atmosphere, they interact with air molecules, creating a cascade of secondary particles that can have significant effects on our atmosphere, climate, and even biological organisms. Cosmic rays are generally classified into two main categories. Galactic cosmic rays, originating from outside our solar system, primarily from distant supernova explosions and other extreme astrophysical events. These are the most common type of cosmic rays and contribute to background radiation on Earth. Solar cosmic rays, ejected by the Sun, especially during solar flares and coronal mass ejections. Less energetic than galactic cosmic rays, but can cause short-term radiation spikes. These are also known as solar energetic particles and can affect satellites, astronauts, and high-altitude aircraft. A smaller but still significant category includes extragalactic cosmic rays, which are believed to originate from even more distant astrophysical sources like active galactic nuclei or gamma-ray bursts. High-energy cosmic rays can damage DNA and cells, leading to increased mutation rates. This has implications for genetic evolution, species adaptation, and potential extinctions. Some studies suggest that past radiation spikes from cosmic rays may have influenced mass extinctions and evolutionary transitions. However, during periods of weak solar activity, known as grand solar minima, during geomagnetic reversals, cosmic rays can penetrate much deeper into the atmosphere, increasing radiation levels on Earth. The weakening of Earth's magnetic field during the Lachamps excursion, combined with grand solar minima, resulted in a tenfold reduction in the cosmic ray cutoff, allowing far more high-energy cosmic rays to reach Earth's atmosphere than under normal conditions. This dramatic increase in cosmic ray penetration had profound atmospheric, climatic, biological, and evolutionary consequences. The world under the Lachamps event was one of dramatic celestial phenomena. With the Earth's magnetic field weakened, the auroras, normally confined to the polar regions, extended to the equator, illuminating the night skies of Europe and Asia with dazzling, eerie displays of red, green, and violet lights. To the Neanderthal, these lights would have been a terrifying sight, an otherworldly phenomenon that they could neither explain nor control. During strong solar storms, intense radiation bursts would have ionized the upper atmosphere, causing dramatic electrical disturbances. In some instances, humans might have witnessed glowing air, much like modern auroras, but appearing in unusual locations, even during daylight hours. The skies may have shimmered with diffuse glows, strange flickering lights, or unusual halos around the sun, phenomena recorded in historical accounts during geomagnetic storms in later human history. Beyond the light show, the effects on the ground were far more dangerous. With higher radiation exposure, the Earth's ozone layer may have temporarily weakened or thinned, allowing greater levels of UVB radiation to reach the surface. For Neanderthals, this could have resulted in severe health problems, including negative genetic mutations. The geographic distribution of the Neanderthals placed them directly in the crosshairs of this increased radiation exposure. Neanderthals primarily occupied regions between 40 degrees and 55 degrees north latitude, including modern-day Western Europe, Central Eurasia, and the Middle East. The higher latitude populations would have faced an intense radiation crisis. With no dense forests or equatorial atmospheres to absorb or scatter UVB radiation, they would have suffered increased exposure to ionizing radiation, leading to reproductive decline. DNA mutations would accumulate, leading to higher mortality, genetic disorders, and decreased fertility, a combination that would have drastically reduced their populations over generations. Cosmic rays are a fundamental part of the space environment and have shaped Earth's atmosphere, climate, and even life itself. While most cosmic rays are blocked by natural protective layers, periods of weakened shielding, such as during geomagnetic excursions or solar minima, can expose the planet to higher radiation levels, influencing climate patterns, biological evolution, and even human technological systems. As mentioned, one of the key amplifiers of this radiation increase was a series of prolonged grand solar minima, which are extended periods of low solar activity when the sun produces fewer sunspots and emits less solar wind. The reduced solar wind weakens the heliosphere, the sun's protective magnetic bubble that shields Earth from galactic cosmic rays, allowing even more radiation to reach the planet. The study identifies a series of grand solar minima spanning the period from approximately 42,400 to 41,100 years ago, with several individual minima occurring within this window. The most significant of these grand solar minima were centered around 42,300 years ago and 41,800 years ago, a 500-year period which coincided with the weakest phases of Earth's magnetic field. The scenario for the Lachamps excursion, combined with grand solar minima, showed greatly amplified impacts, most notably during the winter months, December to February. In addition, there would have been repeated periods of grand solar minima, each a duration of 40 to 140 years. Studies have indicated that magnetic field strength approaches zero during grand solar minima, and the cosmic ray intensity at Earth then approximates the interstellar value found in space. The two most intense grand solar minima occurred during the latter part of the Lachamps event. Assuming the Sun was in an active phase between all the grand solar minima, contemporary observations suggest that within that cumulative total 500-year period, there may have been a total of 180 events. In addition, there is the potential for supersolar energetic particle events, which may have caused short-term UV spikes far beyond normal levels. The consequences of this increased radiation exposure were profound. The influx of cosmic rays dramatically heightened atmospheric ionization, leading to the increased production of nitrogen and hydrogen oxides. These reactive compounds contributed to the destruction of stratospheric ozone, reducing its concentration by as much as 5% globally. With less ozone to absorb ultraviolet radiation, surface UV levels rose by 10 to 15% above current values, with short-lived spikes that could have reached even higher levels during periods of intense solar flare events. The combination of increased UV exposure and reduced atmospheric shielding would have posed a significant risk to both terrestrial and marine life, potentially causing genetic mutations. The increased radiation also had climatic repercussions, particularly in altering global atmospheric circulation patterns. The weakened ozone layer changed the temperature gradient between the equator and the poles, disrupting wind patterns and weakening the Arctic polar vortex. This led to a period of climatic instability, with increased aridification in some regions, extreme rainfall in some places, glacial expansion in others, and continent-wide shifts in weather patterns. In summary, the study presents compelling evidence that the Lachamps excursion and the associated Adams transitional geomagnetic event were a major turning point in Earth's environmental and evolutionary history. The combined effects of a weakened geomagnetic field and a prolonged period of low solar activity led to a surge in radiation levels, ozone depletion, climate shifts, and widespread ecological changes. These findings highlight the importance of Earth's magnetic field in shielding life from cosmic radiation and suggest that similar events in the geological past may have had profound impacts on evolution, climate, and extinction patterns. Around 42,000 years ago, megafauna populations were also experiencing significant stress and decline. By 41,000 years ago, several large Ice Age mammals were experiencing population crashes, particularly cave bears, woolly rhinoceros, steppe bison, and reindeer. Extinctions were accelerating, and genetic studies suggest their population collapsed around this time. In parts of Europe and Central Asia, fossils suggest some megafaunal species were in decline, including the mammoth and large herbivores. At the same time, modern humans were expanding into Europe and Asia. By the time the Lachamps event subsided around 41,000 years ago, Neanderthal numbers had already been critically reduced. The arrival of Homo sapiens, with their technological innovations and population resilience, may have sealed the fate of the last remaining pockets of these archaic humans. Ultimately, the convergence of the Stania pendant and the Lachamps excursion at precisely 41,500 years ago presents an intriguing case for investigating deeper connections between early human culture and environmental forces. While it is difficult to draw direct causal links, the synchronicity of these events suggests that Homo sapiens' expansion into Europe, their interbreeding with Neanderthals, and a major geomagnetic anomaly were all part of a larger interwoven narrative. Whether through genetic changes, cultural shifts, or cultural innovations, it is clear that this was a transformative period in human history. The Stania pendant stands as an artifact of a moment when Homo sapiens were not only spreading across the continent, but also beginning to leave behind records of their world, a world that may have been shaped, in ways we are only beginning to understand, by the shifting forces of the Earth itself.